All right, guys, welcome to Chapter 4. We're going to be looking at applications of differentiation. Now that we know all of our rules for differentiation, we can really differentiate any function. And right now we know some applications as far as like the rate of change goes, but we're going to be focusing on the graph of a function and what the derivatives can tell us about a graph. So that's one of the applications we're going to see in Chapter 4. All right, so application of differentiation. I spelled it wrong. And in section 4.1, we're going to be looking at the maximum and minimum values of a function. Okay. All right. So when we are interested in the maximum and minimum values of a function, sometimes this is called optimization, right? Wanting to optimize our function. You know, especially if we have a function in finance and we're trying to optimize our profits or optimize the amount of material we're using to build a product. There's lots of scenarios where we would be interested in optimization. So to start introducing some vocabulary, let's just draw a generic function on a closed interval. So we'll just say maybe it goes from A to B. All right, so on this function, we can see that there is a high point and there is a low point. Okay, and we call these, the maximum and the minimum values of a function. So to start with our definitions, let's say the maximum point occurs at C. So here's what we would say. We could say something like, for C in the domain D of a function f, let's call this function f, all right, then f of C is called one of two things. Let's introduce the maximum definition first. So f of C is called the absolute maximum. Be right back. All right. Okay, so the absolute maximum value of f, and that's the vocabulary term, so I'll underline it, on the domain D. So f of C is considered the absolute maximum value of f on D if, well, that means that this value has to be bigger than all of the other values. And this value, if it happens at C, would be f of C. So it would be considered the absolute maximum value of f if f of C is greater than or equal to all the function values for all x in the domain. All right. And then similarly, let's say C was not here, but C was here. Okay, and now this was considered, the minimum was f of C. We can talk about the absolute minimum. The absolute minimum value of f on D. F of C is the absolute minimum value. So continuing from this. So f of c is the absolute minimum value of f on D if f of c, now f of c would have to be less than all of the values on the function. So less than or equal to f of x for all x in D. All right, so there you go. And we can, instead of writing n, we have this math symbol, looks like a fancy E. That's a mathematical way of saying n. Okay, so other names that are used for absolute max and mins, we can call them global maximums or minimums. Some textbooks use that notation. We can also call them, just to refer to both of them, we can call them extreme values, or they can also be called extrema. Okay, so these are all synonymous. Okay, so let's draw another picture, because again, this is such a visual section. And we'll draw another function on a closed interval, which I think is important to note, because when we're talking about derivatives, we're always talking about like opened intervals, right? So it's nice to know that we have some closed intervals. So let's draw a cusp. We'll draw a little parabola, a big one, and then we'll go all the way down right here. Okay, so this is just some function f. So looking at this and using our previous definitions, the absolute maximum would happen here, right? Absolute max. And then all the way down here would be your absolute minimum. All right, and then there's some other important points along the way. For instance, this looks like a low point. This is a high point, and this is a low point. So even though it's not the absolute maximum and the absolute minimum, those are still important, because if we were to restrict, let's say, let's call this one at point C, if we were to restrict our focus on just some area around C, like we do when we take the derivative, for instance, we would say it's definitely behaving as a minimum. So these are important, and what we call them, we don't call them absolute max and mins, we call them local max and mins. So here we have two local mins and we have one local max. Okay. All right, so let's define these. So we're going to define the local min and local max. Okay, so we can say that f of c is a local maximum value of f if, and then we have a similar definition, f of c is greater than or equal to, because again, it's a local maximum, f of x. And now this time, instead of saying for all x in the domain, we can just say when x is near C. All right, like we did right here. We highlighted an area around C. Similarly, we can also say we have a local minimum. And if we say we have a local minimum, what would change in the definition? All right, so if f of c is less than or equal to f of x, all right, so that's what's different. So it's less than or equal to. And again, not for all x in the domain because it's a local minimum, but when x is near A. Whoops, excuse me, near C. Okay, and then, near in calculus, it's not a very precise definition. So what we really mean when we say near, we really mean on some open interval if we want to bring it back to calculus, some open interval containing C. Remember, we can make that interval as small as we like, as long as it is containing C. Okay, so let's look at an example. Let's look at the graph of y equals sine x, and let's graph that. We're going to be doing a lot of graphing again in this section, so we're going to have to tap into our pre-calc knowledge. All right, so the range of sine is -1 to 1, and we have, this period of 2 pi, and it goes on forever, right? It can be extended to negative infinity or positive infinity, and that's that. So we're looking at something like this, forever and ever. Woo, I missed it, almost missed it. Forever and ever, okay? So using this graph, we can, once we have the graph, it's pretty easy to tell what the maximums are and where the minimums are. So one way to figure out the maximums and minimums of a graph are to graph it and then just to look, okay? And I think this example is special because we have infinitely many maximums and minimums. And in addition, the local maximum is the same as the absolute maximum. So infinitely many local / absolute maximums. And same thing can be said for the minimums. Okay, infinitely many local and absolute minimums. So again, in this case, the local minimums are the same as the absolute minimums. Okay, let's look at some other examples. So we just saw a case where we had infinitely many extrema. We can have situations. Let's look at the absolute value function. Okay, so something like this. There's our absolute value function. What's the local minimum? We have a local minimum right there, and is it the absolute minimum or a local minimum? It's both, right? Local and absolute minimum. And then what about the local maximum? What is it? There's none, right? Because these are going off to infinity and they always get larger and larger and larger. So there's no one number that's going to be bigger than everything else. This one actually has no maximums, neither absolute nor local. All right. And of course, there's also functions that might not have either. So really basic example is just a graph of a line. The graph of the line, there's no number, and again, we can look at a closed interval. There's no number that's going to be the maximum or the minimum, because you can choose any point on the line like this, and there's always going to be a point that's bigger. You can choose any point on the line, and there's always going to be another number that's bigger. So in this case, there's no maxes or mins. Okay, and then finally, just to give us another example of a function that doesn't have maximums or minimums, let's look at our tangent function. Do a quick little sketch. All right, negative pi over 2 to pi over 2. And what we know about the tangent function is we have all of these periodic asymptotes, right? Whoops, my curvature was off on that one. And what's the maximum and minimum? Again, no max or min. Okay, so that can also look like an asymptote. Okay, so let's start to talk about cases, let me go back up here, where absolute maximums and absolute minimums are guaranteed. So these are the situations. So in order for absolute maximums and absolute minimums to be guaranteed, first of all, f has to be continuous. So f has to be continuous. And f has to be on a closed interval. If we have that, then we're guaranteed to have an absolute maximum and an absolute minimum. Let's look at our other examples. All right, down here, this was not, these two are not on a closed interval, right? They're essentially on negative infinity to positive infinity. So we didn't have any local mins and local maxes. Here, we're not continuous. So because we're not continuous, we can have those asymptotes and we would never get a max or min. Even in between, if we were just to look at one period, we're going from negative pi over 2 to pi over 2. That's an open interval. We're not including those endpoints. Okay, so let's write some of that down. So that's called the extreme value theorem. And we'll write down all the qualifiers or quantifiers. Qualifiers. All right, the extreme value theorem. So first, we want f to be continuous. So if f is continuous, on a closed interval, that's the other important part. Let's call the closed interval AB. Remember we use brackets when it's a closed interval, parentheses when it's open. All right, so these are our two criteria. This is our hypothesis. If those hold, then we have the extreme value theorem. Then f has an absolute maximum value and the value is on the function. So it's not where it's happening, but it's the value on the function, the absolute maximum value f of c, and an absolute minimum value f of d. Okay, at some numbers, c and d, where c and d are in this closed interval a and b. Okay, so some numbers in that closed interval a and b. Okay, so again, what this is saying, let's create this situation. So first we need a closed interval, and we can just go from a to b. Okay, and you know, wherever we start to wherever we finish, however you draw that line, all right, maybe you're just going straight across. You would have your minimum and you'd have your maximum, okay? Maybe it would be a horizontal line. Those numbers would still be your minimum and maximum because the definition just says less than or equal to, greater than or equal to. Let's say you tried to get more creative. Okay, and you did whatever you wanted to do with your function. Oops, that's not a function anymore. Let's make sure it's a function. You try to go really high and really low and stuff like that. No matter how you draw it, you're always going to end up with an absolute maximum minimum because the function is continuous and it's on a closed interval. All right, so that's why it works. And let's do here. Let me write that. This is a continuous function with a closed interval. So we've definitely seen counterexamples with open intervals. That's what we spent that first time talking to, closed interval. I want to show you an example of a closed interval with a not continuous function. So here's our closed interval still. And let's say this is our discontinuous function. And right at the top, we have our point of discontinuity. And if we were to take a microscope, if we were to zoom in on this point, you could choose a point and you could say, okay, this is the biggest point. But then, since it's open at that point of discontinuity, we can get a little bit higher. And now you can say, okay, this is the biggest point. But then we can get a little bit closer to the point of discontinuity, and we'd still get higher and higher and higher and higher. There's definitely a limit, right? But there's no single value on the function that's bigger than everything else on the curve. So it's not a continuous function. We still have a closed interval. But now there's no maximum. All right, there's a limit, right? This would definitely be the limit, but a limit isn't a value on the function. To be a maximum, you have to be on the function. So there's no one value that's going to be bigger. We can choose a value, but getting closer to this point of discontinuity, we can find another point. And then we can find a higher point and a higher point and a higher point and a higher point. And we can get closer and closer, and there's never a maximum, okay? So up here, definitely, because we fulfilled the hypothesis of the theorem. Here, this wasn't fulfilled, so we were not guaranteed a maximum point. Okay, so again, we're just highlighting that we need both. We need it to be a continuous function, and we need to have it be a closed interval. All right, so what we know, we'll go back up to this little example. Some things we know about when we have extreme values like this, we are experiencing some sort of change of direction, right? And we've talked about this a lot. And if we were to draw a tangent line at that point, high point or low point, the tangent line would be horizontal. And what do we know about the slope of the tangent line? It's 0. So the derivative is 0 at that point. And that's what Fermat's theorem talks about. So we're going to talk about Fermat's theorem next. Okay, so if f has not an absolute maximum, but a local max or min, at the point C, and if f prime of C exists, then f prime of C equals 0. All right. And again, we've been talking about that for a while, right? We know that at those local minimums and local maximums, the slope is 0. We're calling this C. That means f prime of C has to be 0. All right. And I do want to say that, again, it's just so much fun to tear apart these theorems because every word is important in theorems. This term local max, Fermat's theorem is only for a local maximum. For instance, if we set up the situation where we have a closed interval and a continuous function, well, we can just do a straight line on this closed interval. We have an absolute max, and we have an absolute min, okay? But it's not a local max and local min. And we see at those points that f prime of a definitely doesn't equal 0. Okay, so Fermat's theorem is only for local minimums and local maximums. Okay, so this is actually a fun little proof. So we're going to prove Fermat's theorem. Okay, so proof, we're going to assume all of the points in the hypothesis. Okay, so we have to assume, let's go back up to our theorem. We have to assume that f has a local max or min at C. All right, and then we also have to assume that f prime of C exists. Okay, so the proof it works, we're going to assume these two things hold. Then we have to show that the derivative is 0. All right, so let's go for it. So let's start off by expressing or assuming everything in the hypothesis holds. So suppose f has a local, we'll start with maximum. Okay, so what does that mean? So if we're a local maximum, it means that f of c is bigger, greater than or equal to all f of x if x is near c. Okay, if we wanted to bring in our calculus vernacular, we could say x is sufficiently close to c. Do you remember that terminology from chapter 2? Okay, so if h is close to 0, do you guys see where this is going? All right, remember we have to try to prove the derivative. So we're going to start introducing some terminology that has to do with the derivative. All right, so we have c right here. F of c is a local maximum. So if this is c plus h, then f of c has to be bigger than f of c plus h because it's a local maximum. All right, and that's kind of setting up our limit definition of the derivative. So I'm going to subtract f of c from both sides. Okay, and then let's see, we're on this side, so let's make sure less than or equal to is being pointed away from us. And then let's do two cases. Let's do one case where h is bigger than 0. So if h is greater than 0, so it's a positive number, we know we can take an inequality and divide it by a positive number, like h, and the inequality will stay the same, right? And 0 divided by h is 0. Okay, so if this is true, well, the other part that we have to assume, this is what, we did all that just from this aspect, and now we're going to bring in the fact that f prime of c exists. So that means the limit of this exists. And let's see, h is greater than or equal to 0. So we'll do this. As we're approaching h from the right, that means this expression, this limit, still has to be less than or equal to 0, since the limit exists. Okay. And that's exactly what f prime of c is by the limit definition. Well, let me back up. This is the limit of f prime of c, right? And because it exists, the right-hand limit and the left-hand limit are the same. So there's that piece of the puzzle. Okay, and now that is less than or equal to 0. So just kind of putting together what we just discovered, f prime of c is less than or equal to 0. All right, so not bad. So we want to show that f prime of c is exactly 0, not just less than or equal to 0. And what we actually have to do is we have to come in and say, now let's suppose h is negative. I'll do it in a different color. So now, if h is less than 0, where we stopped, we stopped right here, right? Let me remind you. In our notes, we were right here. So we went back to that point, and now our new assumption is that it's less than 0. And what happens when we divide by a negative number? We flip the inequality. So now that c is negative, if we divide both sides by that negative number, we have to flip that to greater than or equal to 0. Okay, and then our whole argument repeats. We can come in and we can take the limit as h approaches 0, this time from the left, and we get this. So then f prime of c, again, is equal to this limit, since it exists. Since it exists, it means it's equal to the left-hand limit. And this expression, the left-hand limit, is greater than or equal to 0. Okay? So f prime of c is greater than or equal to 0. We also know that f prime of c is less than or equal to 0. So if we are greater than or equal to 0 and less than or equal to 0, there's only one option. There's only one intersection point on those two things. And that's when f prime of c is exactly 0. So we just proved what we wanted to show. We wanted to show that the derivative was equal to 0. Okay, so that was for the maximum, and there's a very similar argument for the minimum. The only thing that changes for the minimum is this step right here. If it was a minimum, then f of c would be less than or equal to f of c plus h. But everything else is exactly the same. Okay. Let's talk about what we can do with Fermat's theorem and the limitations of Fermat's theorem. All right, let's suppose f of x is equal to x cubed. Okay, so let's say we wanted to go backwards with Fermat's theorem. So let's take the derivative of f of x, and let's find the zeros of the derivative. So in other words, let's find all the points c where the derivative is equal to 0. So where does 3x squared, or 3c squared, if you will, equal 0? It happens at c equals 0. Okay, so we have a derivative at c, and that derivative is 0. So is there a local min or max at x equals 0? Okay, so do you see what we're doing with Fermat's theorem? We are going the opposite direction. So we have, keep going. All right, we just found that f prime of c is 0 when x is equal to 0. Does that mean we have a local max or local min at 0? And the answer is no. Do you guys remember what the graph of x cubed looks like? Something like that, where it does a swivel. And at that swivel, that tangent is 0. The slope of that tangent is 0. Is that a local min or max? No, it's not. So we call that, kind of the converse, right? Going the opposite direction. So no. So is there a local min or local max at 0? No. The converse, or the going backwards, of Fermat's theorem is not true. It only goes one direction. If you are a local min or local max, then your derivative is 0. Okay, the only time we can go backwards is in an if or only if statement. So let me write that out, because that's important to know, especially as we're getting higher up in the math world. So it's not I'm going to abbreviate theorem. Fermat's theorem is not an if or only if statement. If and only if means you can go frontwards and backwards. But since there's only one if in Fermat's theorem, it only goes one direction. Okay, but this C is important because it does make the derivative 0. So what we called C in our example, C equals 0 from this example, is called a critical number. And we're going to define that right now. Okay. So another definition. Definition. A critical number of a function of a function f is a number c in the domain of f such that and there's two situations. Either f prime of c equals 0, okay, or f prime of c doesn't exist. And people always forget this last one. Okay. So there you go. And remember, there's lots of reasons why derivatives don't exist. They could be approaching an asymptote. We could be having a cusp. Remember how some functions have a cusp like that? This derivative would not exist, but it's definitely a local max, right? Absolute values, when it's a sharp point like that, that derivative doesn't exist, but it's definitely a local minimum. So critical numbers include both. Where the derivative is 0 or where the derivative doesn't exist. Okay, so let's practice that. Let's find the critical numbers of the function g of x equals to the cubed root of 4 minus x squared. Okay, and now remember critical numbers, it has to do with the derivative, right? So to find critical numbers, we have to take the derivative and figure out where the derivative is 0 and figure out where the derivative doesn't exist. All right, so our first step is to take the derivative. All right, let's use the chain rule on this one. Write that cubed root as an exponent. Derivative of the outside function first. Then subtract 1. And then we take the derivative of our inside function. Okay? And we'll clean it up, of course. Especially in this case, it's really important to clean it up, and if it belongs in the denominator, put it in the denominator. And you'll see why in a second. Okay, so this has a negative exponent. This is the only thing in the numerator. I'm going to bring the negative sign out front. So we have a 2x right there. Downstairs we have a 3. And then we have a 4 minus x squared to the 2/3. Okay, so we have to figure out where we're 0 and where we're undefined. So when dealing with fractions like this, or rational expressions, the derivative is 0 when the top is equal to 0. Right? Because 0 divided by a number is 0. Okay, so there you go. So let me see. Some other criteria. Let's go back up to our critical numbers. Also, the numbers have to be in the domain of f. Okay, so before we start solving, let's take a look at this. Are there any domain restrictions in our function? No. The domain is all real numbers. Do you remember the sign for all real numbers? It's a fancy R, right? Because the cubed roots can be positive or negative, and it can be 0. So that's all the real numbers. Okay, so when is 2x equal to 0? When x is equal to 0. Good. All right, so that's a critical value. X equals 0 is a critical number since f or g prime of 0 is 0. Okay, so let's write that out. X equals 0 is a critical number since g prime of 0 equals 0. All right, and then where is g prime of x undefined? I'll just write d and e. Okay, and g prime of x, it does not exist when our denominator is 0, because we're not allowed to divide by 0. So we want to know if and when the denominator is 0. And again, we're taking a cubed root, so we don't have to worry about, negative numbers there. Okay, so let's think, when is this expression going to be 0? Well, not the 3. So we can divide both sides by 3. So we would want to know when 4 minus x squared to the 2/3 is 0. Well, if we raise both sides to the 3/2 power, when is 4 minus x squared equal to 0? And we can solve that, right? We can bring the x squared over and we can take the square root. And this is going to happen at plus and minus 2. So we have 2 more critical numbers. So x equals -2 and 2 are critical numbers. And the reason why, critical numbers, the reason why is g prime of -2 and the derivative at 2 are undefined or do not exist. However you want to say it. Okay, so where we're going with all of these pieces to the puzzle is we're eventually going to be able to have an algorithmic way, so a step-by-step way, of finding absolute maxes and minimums of a function, right, with some given criteria. And we're going to be going over that in part 2 of our video.